Today we are going to learn about optimizing PyTorch tensors with automatic differentiation. We will explore how to use PyTorch's Autograd feature to compute gradients and optimize models effectively. Welcome to our video on optimizing PyTorch tensors with automatic differentiation. In this video, we'll delve into how PyTorch's Autograd feature can be used to efficiently compute gradients, which is crucial for training neural networks. You'll gain a foundational understanding of automatic differentiation and learn how to set up tensors with requires_grad, perform backward passes, and use Autograd for parameter optimization. By the end, you'll be equipped with the skills to implement simple gradient descent, monitor and visualize gradients, and troubleshoot common issues in Autograd.
Automatic differentiation is a computational technique used to efficiently and accurately evaluate derivatives of functions. Unlike symbolic differentiation, which manipulates mathematical expressions, or numerical differentiation, which approximates derivatives using finite differences, automatic differentiation breaks down computations into elementary operations and applies the chain rule to compute derivatives. This technique is especially powerful in the context of training neural networks, where derivatives are used to update model parameters through backpropagation. PyTorch's Autograd module automates this process, allowing for seamless computation of gradients. This automation not only accelerates model training but also reduces the potential for human error in derivative calculations. Understanding the nuances of automatic differentiation is crucial for anyone looking to optimize neural network performance.
In PyTorch, tensors are the core data structure, and enabling gradient tracking is a key step for optimization tasks. The requires_grad attribute, when set to true, indicates that PyTorch will track all operations on the tensor and store the gradient of the resulting value with respect to the tensor. This is essential for calculating derivatives during backpropagation. For example, when you create a tensor by calling torch.tensor with requires_grad equals true, any subsequent operation on this tensor will be tracked, and its gradient can be calculated. This capability forms the backbone of neural network training, allowing for dynamic computational graph creation. By understanding how to properly set up tensors, you ensure that your models are ready for efficient optimization. The backward pass is a critical phase in neural network training where gradients are computed. In PyTorch, this is achieved using the backward function, which calculates the gradient of a scalar loss with respect to all tensors with requires_grad equals true. When you call backward on a tensor, PyTorch traverses the computational graph in reverse and applies the chain rule to compute gradients. This process updates the grad attribute of each tensor, storing the computed gradients. Backward passes enable the adjustment of model parameters, driving the learning process. By mastering backward passes, you can optimize your models more effectively, ensuring they learn from data as intended.
Autograd plays a pivotal role in parameter optimization within neural networks. After computing gradients with backward passes, these gradients are used to update model parameters, reducing error and improving model accuracy. In PyTorch, this update is typically handled by optimizers like SGD or Atom, which adjust parameters based on the gradients and learning rate. The optimizer.step function applies these updates, optimizing the model. By leveraging Autograd, you automate the gradient computation process, streamlining parameter updates and enhancing model performance. Understanding this process is crucial for effective model training and optimization. Gradient descent is a fundamental optimization algorithm used to minimize a function by iteratively moving towards the steepest descent. In the context of neural networks, it involves adjusting model weights to minimize the loss function. In PyTorch, you can manually implement gradient descent by computing gradients with backward and updating weights using the gradients and a learning rate. For instance, you might subtract the product of the learning rate and the gradient from each weight to update it. This process is repeated iteratively, refining the model's accuracy. By understanding and implementing simple gradient descent, you gain insight into the mechanics of model optimization.
Monitoring and visualizing gradients are essential for diagnosing and improving neural network training. Gradients indicate the direction and magnitude of parameter updates, and anomalies can lead to poor model performance. In PyTorch, tools like TensorBoard and Matplotlib allow you to visualize gradients, providing insights into the training process. By plotting gradients, you can detect issues like vanishing or exploding gradients, which hinder learning. Addressing these issues through techniques like gradient clipping or normalization can enhance model training. By mastering gradient monitoring and visualization, you ensure your models train efficiently and effectively.
Handling non-scalar outputs in backward passes presents challenges, as backward requires a scalar to compute gradients. PyTorch addresses this with the vector Jacobian product, allowing you to specify a gradient argument when calling backward. This argument acts as the gradient of the output with respect to the scalar, enabling gradient computation for non-scalar outputs. For example, if a model outputs a vector, you can pass a tensor of the same shape to backward to compute gradients. This technique is vital for complex models with multidimensional outputs, ensuring they can be optimized effectively.
Autograd is a powerful tool, but issues can arise during its use. Common problems include incorrect gradient calculations, missing gradients, or memory leaks. To troubleshoot, ensure tensors have requires _grad equals true and that backward is called after loss computation. Avoid modifying the computational graph in ways that could prevent gradient tracking. Utilize PyTorch's hooks for debugging and verify gradient values to avoid anomalies. Adhering to best practices and understanding common pitfalls can prevent issues, ensuring your models perform as expected. By mastering troubleshooting, you enhance your ability to optimize neural networks effectively.
In conclusion, we've explored the essential role of automatic differentiation in optimizing PyTorch tensors. From understanding the basics of Autograd to implementing gradient descent and troubleshooting common issues, you've gained valuable skills for training neural networks. The knowledge of gradient computation and parameter optimization is crucial for enhancing model performance and ensuring efficient training. As you continue your journey in deep learning, remember to practice these techniques and explore their applications in more complex models. Thank you for joining us, and happy coding!